In this video, I will talk about potential energy, the Taylor series, and how we can use the Taylor series to approximate the potential energy around the minimum. So in this case, I have done a graph where I have the potential energy of a system, and this is as a function of x. Now I'm using x, it may be r, it may be theta, it doesn't really matter what the variable is, so long as I have a minimum of the potential energy as a function of a variable. Now I've written here what is the first three terms of the Taylor series, and this is the function x minus x naught, and I have this is equal to the value of the function at x naught plus 1 over 1 factorial the derivative at x naught times x minus x naught plus 1 over 2 factorial the second derivative of the function f at x naught times x minus x naught squared, and the rest of the terms follow. Now this is the application now of the Taylor series here. Let's say this is the point where I have the minimum, so this will be x naught in my case. Now I'm gonna do the value of the potential energy is equal to the value of the potential energy at x naught. Now I'm gonna show you on the graph what that is. So this is, I need to find the variable at x naught, x equals x naught, and then I have to see what is the potential energy at that point. So this here, this will be EP at x naught. Okay, so I'm starting my Taylor series for my potential energy from here, which makes sense. That's the minimum. Now the next term is 1 over 1 factorial is just 1. And then I have the derivative of the potential energy at x naught times x minus x naught. Now I'm gonna think about this. When I have the derivative of my potential energy, since I am expanding the potential energy around the minimum, I know that at the minimum at x naught, the derivative is going to be 0. When you have a graph, the derivative essentially is the slope, and you can see the slope here is the tangent to the curve is completely horizontal, so the slope at x naught is 0, and that's why this second term goes away. Now 1 over 2 factorial is simply 1 over 2, and then I have the second derivative of the potential energy times x minus x naught squared. I will neglect the rest of the terms. Now if this is the kind of the potential energy that I have in my system, then this second derivative will not be 0. And I can tell you how you can think of the second derivative. As I said, the slope, the first derivative represents the slope, and the second derivative essentially is the slope of the slope. Now it may be a little bit confusing if you try to think of the slope of the slope. A way that I think about the second derivative is the change of the slope. It's more or less, it's equivalent really to thinking of the slope of the slope. But if the only thing I need to know if the second derivative is positive or negative, looking at the change of the slope also works. So if I go a little bit before x naught, I can see that the tangent line would be here, and I would have a negative slope. Then if I go a little bit after x naught, the tangent line would be like this. I will be aligned with a positive slope. So how does the slope change? It goes from a negative number to a positive number, and that means that the slope is positive. So the change in the slope is a positive number. That means that according to this graph, the second derivative of the potential energy at x naught will be a positive number. Okay, and whenever the second derivative is a positive number, actually that's how you know that you have a minimum. All right. Now, so this is important to keep in mind. Let's say that what I have is I have a case where the potential energy is symmetric around the around the vertical axis. Essentially, I want to talk about the case where x naught is 0. In that case, I will have EP of x is equal to EP at x naught plus 1/2 the second derivative. Okay, so I said that I was gonna make the x naught 0. Well, let's make it 0. So this one is gonna be 0 EP, the second derivative of the potential energy at 0, and then this will be times x squared. Now, as I mentioned before, I know that this is going to be a positive number based on the shape of the potential energy graph. Now, we have here an expression 1/2 times a number x squared. Where we have seen this in introductory physics is when we talked about the potential energy of a spring. And we if you use the ideal spring model, then the potential energy of an ideal spring, okay, is 1/2 k x squared, or if you want, really with x I mean the stretch or the compression. Now, if you do some pattern matching between this expression and this expression, you can see that you have 1/2 x squared. So essentially, the second derivative of the potential energy at 0 is the equivalent of the spring constant. So this k of an ideal spring, this will be the spring constant. And back to this expression, the Taylor series can give you the spring constant if you had a potential energy due to a spring mass system. Now I want to talk about something. I want to draw something on the graph. This is the red line is the actual potential energy of the system. When I use a Taylor series to approximate the potential energy around x naught, and when I use essentially these two terms, I am approximating the potential energy with a parabola. Okay, so this is a parabola. The red one is not. What is the red one? As I said, the red one is the actual potential energy of the system. The orange line is a parabola. It is a 1/2 k x squared graph. Now, what the Taylor series is telling us here is that you can use a parabola to approximate the actual potential energy. So let me change that to approximate. Okay, it's not exactly equal. So this is my parabola, and this is the actual, the not parabola. This would be the red line. Now, I want to mention something about the Taylor series. Remember that when we do an expansion of the function f around x naught, we do have to constrain ourselves to values of x around x naught. So say in this case x minus x naught will have to be a small number. Okay, and with this I mean when you do the Taylor series expansion, this expansion is valid only if you are very close to x naught. You have to remain very close to x naught. Now, what does that mean about what I did here about the potential energy of a system? Essentially, this constraint of the Taylor series is telling me that if you want to use a parabola to approximate your potential energy, you can do it, but your approximation with the parabola will be accurate so long as you remain close to x naught. And this is what I'm showing here with the orange line and the red line. The orange line is closer to the potential energy of the system when you stay around x naught, but as you start deviating more and more from x naught, the deviation between the two becomes greater and greater. So this is something important to keep in mind. You can use the Taylor series to approximate a minimum of the potential energy, but when you do it, make sure you stay around that point. This approximation is not valid forever. It's not valid for any value of x. You have to stay around the minimum.